All right. Hi, everybody. Continuing our lecture topic 2 on vision. We now have 2.3 of 7 subsections. So in the last, in 2.2, we talked about the anatomy of the retina and the rods and cone cells and how those work and how they operate under different levels of light. So we are now going to be talking about in photopic vision, when there is enough light for our cone cells to be active, how do those cells activation result in the perception of color? Or what I'll distinguish the term hue, H-U-E, as what we usually talk about with color in light. So the hue is basically directly related to the wavelength of light. Okay, so now here's, when I talk about audition, you're going to hear me bring this up again. But the concept of white light and white noise are the same general idea, in that when we talk about what we describe as white, the color in light or the hue, it's actually what our brain interprets when there is the combination of all wavelengths of light with roughly equal intensity across the entire visual spectrum. So if we interpret sunlight as white, it's not exactly white. There's some yellows to it, or it depends on, how much atmosphere it moves through. But if we assume white as the source of light, so whether that's sunlight or artificial light, and we use a prism then to separate the components of that light, that's when we get the full rainbow spectrum. So read through, Roy G. Biv, if you learn the colors of the rainbow, these represent all of the wavelengths of light in the visible spectrum. And of course, this is continuous also. So it's not like it's red for a little bit and then it stops and becomes orange and then there's a discrete step to yellow. These are continuous wavelength, and it's just the way that our brain interprets those wavelengths and categorizes them with labels like red, orange, yellow, that we perceive them that way. So again, all of white light can be decomposed if you have a prism into the individual wavelengths. You can also take light at specific wavelengths and combine them and end up with all these sorts of different perceptions. And so white light in this case could be the result of combining red, green, and blue lights at specific intensities. Now, when I say, oh, this is the entire visible spectrum, you say, well, there's only a red, a green, and a blue light. That's where things get really interesting, because we have 3 types of cone receptors, and they happen to be very well tuned to what we think of as red, green, and blue. So because all of our color vision is based on the relative activity of these 3 types of cone cells, then we can recreate human perception of white light by combinations of those 3 inputs. So we'll get to more of that in this lecture, but just for now, white light, just like white noise, is our descriptor for all of the energies within the visible or audible spectrum. Good. Okay, now you have to think of light in terms of 2 different kinds of categories. One is emitted light or projected light. Okay, so if light comes from a light source, it will have a certain color quality when it reaches your retina. If that light then strikes an object and reflects off that object and then reaches the retina, now we have some slightly different rules we have to think about if you're saying I'm looking at an object versus I am looking at the light that strikes my retina. Okay, so let me distinguish the 2. So in order for us to see something and say, hey, that is a certain color. I see this potion drink here, and we say that is red. Why do I say that's red? So here's what happens. So there is light in our environment, if we can see anything. That's either, the sun or an interior source. I've got the light on in this room here. I've got the light projected from the screen, and I've got lights from my open windows here next to me. All right, so there's that light in the environment. It's composed of many wavelengths. If it's white, you can say, well, it's all of the visible spectrum wavelengths or close to that. And so then that light strikes an object, and based on the material properties of that object, there will be a certain amount of a certain portion of that light that strikes it will be absorbed, and what is not absorbed is reflected back. Okay, so there is what we call a subtractive process in terms of when an object is struck by light. Here's the sun, strikes this object. Some of that light is absorbed. The energy becomes heat, or it becomes whatever in this material. The remaining light that is not absorbed is reflected off. Okay, now the light that's reflected off, this is the light that our retina has access to. We don't get to see the light that strikes this thing. Okay, and we can turn and look. We can turn and look at it, but we're not going to see the object, right? So the light strikes this object, whatever is absorbed, and then some is reflected back. That's what our eyes can pick up. So when we look at something and we say that looks red, what I'm really saying is the white light in this environment strikes this material, and this material absorbs the wavelengths of light that are on the shorter end, the blues, the greens, the yellows, and it reflects back the reds. So the reds are not reflected. I'm sorry, the reds are not absorbed by the material. Maybe this is a better, the hard plastic on top here. The reds are not absorbed from the white light that strikes this. The reds are reflected back. That's what's available for my eye. Okay, so when an object appears to be a certain color, what you're saying is it has a chemical property, that surface has properties such that it absorbs the wavelengths of light that are not what you see. What you see is what's reflected back. So it's essentially saying this plastic right here is resistant or it is absorbent of all wavelengths of light except the reds. Okay. All right. Okay, good. So some are absorbed, some are reflected. Right, there we go. So I mentioned the term subtractive mixing, and a good example of this is with paint. So if you think about like house paint, right? So, you know, maybe at school, in school or whatever, you're, or just exploring on your own, you found out, well, hey, if I mix blue paint and yellow paint, I get green paint. So how does that work with what Ferris just said, right? Okay, so imagine that we've got SM and L, short, medium, and long wavelengths of light. Let me just review where that came from here. So I'm going to go back to the previous, just to make sure we're on pace here. Oh, I had one right there. Okay. All right. Short, medium, and long wavelengths of light. Remember, the shorter wavelengths are the higher energy. And what I had said in the previous lecture, one way to remember that is the difference between a DVD player, which uses a red laser, and a Blu-ray player, which uses a blue laser. And so the blue laser having a shorter wavelength than red and higher level of energy, it can also sample more data, essentially per beam time. I'm not sure what the terms are there, but blue, as it, you know, we know a Blu-ray player can read more data from a disc than a DVD player, and that's again because the shorter wavelength allows more data to be essentially pinged, you know, to determine is there more digital data can be included, you know, on the surface. Again, okay, so short, medium, long, in a general sense. We're just going to talk about receptors that way. And so if I have a chemical, this paint, which has the property that it absorbs long wavelengths of light very well, does a good job of absorbing those long wavelengths. The medium ones, it sort of absorbs them, but it absorbs none of the short wavelengths of light. It reflects those off. So this substance appears to our eye to be blue because it's reflecting primarily the shorter wavelengths of light, this end of the spectrum, right? Okay. So let's say similarly, let's take yellow paint, And yellow is that mysterious color here, kind of between green and red, right? So that's how our brain interprets wavelengths of light that are at about, 560, 570 here. So how does it work if it's paint? In order for us to get that yellow hue to strike our retina, we need to have some absorption of the short wavelengths of light and some absorption of the excuse me the medium, sorry, entirely absorbing the short wavelengths of light. There's no blue in this, reflecting mostly the longer wavelengths. So I guess this is a little screwy because the longer wavelengths are not colored yellow, but yellow is closer to a longer wavelength than a shorter wavelength. And it's reflecting back some of the medium as well, okay? So here we have, if you think of it this way, this is a chemical that absorbs long wavelengths of light. This is a chemical that absorbs short wavelengths of light. So if you think of just the chemical properties of these two substances and we combine them together, now we have a substance that both absorbs the short wavelengths of light because of this component and the long wavelengths of light because of, sorry, vice versa, because of the other paint. So when I combine those two chemicals, I have something that absorbs short and long and reflects to some extent back the medium wavelengths of light. So then that's how it looks green. Okay. So again, this is something called a subtractive color mixing. I guess I don't have that as a buzzword here, but so I won't test you on it, but it'd be the kind of thing that you talk about additive versus subtractive color mixing. Additive is we're going to take the source of light, we're going to add different wavelengths to it, we're going to combine them. And subtractive is usually talking about mixing chemicals or mixing surfaces that have these reflective and absorptive properties. So you're taking wavelengths of light out of the image when you're mixing in chemicals that absorb that light. Okay. So following from that, I'll go this way. Following from that, there's a lot of common things we can now start to think of in terms of their chemical properties or in terms of how much they reflect different wavelengths of light. So a tomato is red because it reflects mostly the longer wavelengths of light and it absorbs mostly the shorter wavelengths, okay, most of these. White paper looks white because it equally absorbs or equally reflects, I should say, all of the wavelengths of light. And black paper as the absence of reflection. So white paper reflect everything, black paper reflect very little, absorb most of the light. Okay, so it appears black. Our perception of black, it's not that you've probably heard this before, black isn't a color, white isn't a color. They are the combination or the absence of all wavelengths of light. Okay, so combination of all wavelengths, everything is reflected. I'm going to get the perception of white, and similarly black if it's all absorbed. Yeah, and then okay, good. So I think that's pretty good here. All right. Now, red, green, and blue. I mentioned a couple slides ago. I said, hey, there's a special relationship here. Why do we use red, green, and blue? You may also be thinking, hey, red, green, and blue, you mean like the pixels in my computer monitor? And I don't know if you can do this. You know, you get close enough. Our monitors are mostly higher resolution that don't allow you to do this so much anymore. But I remember as a kid being just like totally blown away that if you get really close to the TV, you can see the pixels, the red, green, and blue elements of the light of the pixels that are emitting light. And it's literally the combination of just those three hues, red, green, and blue, and the relative intensity of each of them that creates the entire spectrum of emitted light colors that we think of that, that a TV could produce or a computer monitor. So why red, green, and blue? It's because that's the peak sensitivities of the three different types of cones that we have on the retina. So remember, we have one type of rod, and our retina is mostly rods. We have cones mostly densely packed at the fovea and the foveola, that very center of our retina. And of those cones, we have three different specialized types. And those three specialized types activate with different intensities based on the wavelength of the light that's available, okay? So the sensitivities, just like we talked about with the rods and the cones, have peak sensitivities. Remember the Purkinje shift, the Purkinje effect that happens, you know, when the light goes down at the end of the night and your vision transitions from primarily cone-based vision, and the reds are vibrant, and then the light goes down and it gets darker and darker, and your rods take over the primary source of vision, but they're sensitive to more the blue end of the spectrum. So effectively what happens are the red end of the spectrum gets lost. It essentially becomes just like if I were to shine my TV remote into your eye, you don't see it, right? So if cones are inactive, we don't have any visual system that is sensitive to certain reds. So a very bright, vibrant red flower in a bright sunny day, at night when you're dark adapted and you're using your rods, it's going to look black. And the blue aspect, so blue flowers, you know, the green elements of foliage outside at night, the closer to the blue end, I should say, than the reds, these are going to be relatively more vibrant when your rods are primarily responsible for vision. So similarly, where we talked about rods having a sweet spot, cones in general having a sweet spot, the cones are specialized, and each type of special cone has a sweet spot. So 430, 530, and 560. We will, just to make things easier for us to wrap our heads around it, we're going to call these blue, green, and red cones, but make sure, you know, don't get confused into thinking that these cones are, like if you were to look at them on the back of a retina under a microscope, they don't look blue. They're not hues. The cells themselves don't have these hues. Also, the cells themselves are not only sensitive to hues in this range. It's just that they're maximally sensitive to hues that we describe by these colors, okay? So the blue cone is still getting activity, you know, anywhere where we see this curve. It just gets the most activity if you shine a 430 nanometer wavelength laser into my eye, okay? All right, so these three sweet spots here. Okay, now, with those three types of cones, and the combination of activity among those three types of cones, this creates all the data that our brain needs. It's everything that your brain needs to create the perception of hue, of colored objects. And we call this the theory of trichromacy. Tri meaning three. We've got three cones, most of us. And we combine the input from those three to get our entire visual experience. Okay, so let me back up for a minute and say, yeah, we got these three, but there's two different ways to express a hue in the physical world that are indistinguishable to the human eye, okay? So, you know, what do I want for this one? Boring. No, not that. Use that one again. Just think about this. There's two of them. Two different ways I could create green, okay? So the first, I already kind of mentioned this, I could get either a filter, you know, on a light. I showed you in the previous lecture how you can buy a cone sweet spot filter. Most visible is in the green range. I could get a laser, you know, I could get a laser that has a light emitting element that very precisely emits, you know, a specific wavelength of light at 500 nanometers, let's say. So if I have that laser beam and I shine it in my eye, I'm going to say, yep, that's green. Okay, that looks green to me. Now, let's say I don't have a laser that is exactly 500 nanometers, but I have a TV screen or I have a computer monitor. And I find out, well, if I can adjust the relative intensity of the reds, the greens, and the blues in my pixels on these light emitting elements, I can create the perception of green that is literally indistinguishable from a laser beam. Okay. And why is that indistinguishable to a human? It's because they cause the exact same activation of our cone cells. The exact same pattern of activation would be present whether you have a pure beam of light or where you carefully construct a balanced combination of red of 420, 560, and 640, or what did I have here? There's slightly different numbers. You see 430, 530, 560, slightly different numbers than these. I don't know why the numbers are slightly different, but just believe that I guess they can be slightly different and it still works. All right. And there's again, you know, the a pixel here, red, green, and blue. Relative intensity of these light emitting elements is how we create the entire range of visible light from our, you know, from our two-dimensional displays, pixel arrays. And so yeah, we get the full range of colors there. Okay, so here, this is a graph that kind of shows across the visible spectrum the relative amount of activity we get in our short wavelength blue, medium wavelength green, and long wavelength red cone receptors. Okay, so here I've got a little animation here. So here's my laser beam of light. Okay, so right at about 460 or 455 or something. And what do we get if I shine that laser beam of light very precisely tuned to this wavelength? I get, let me get my colors out. Hang on. Annotate, draw. I get this much activity in my short wavelength. So imagine this is sort of a representation of the amount of neural activity. The larger the cone cell here, the more neural activity it's sending to the brain. So oh, I should use blue for that, shouldn't I? Let me undo, and then let's do it with blue. Okay. All right. There we go. Blue right there. So there's the blue level of activity, which is going to be large. Okay, so we call that a lot of neural activity. The green, the medium wavelength receptors are going to be active, but at a lesser extent, right? So we can see then like a medium amount of activation here. I don't know what I'm doing with this. A medium amount of activation that goes to the brain. And then, of course, our long receptors. And we're in this range. It's getting pretty close to the blues. So, you know, we have the least amount of activity here in our long wavelength receptors, or the red ones. But this relative amount of activity is how your brain interprets what is the hue that it's seeing. And your brain will then, constructing this image, will create something that looks to you to be in this blue region right here. Okay, so here's how the pixels work, right? So I've got those three levels of energy. And, okay, I'll go back to mouse. There we go. Now, I could also have a pixel that is specifically tuned to exactly whatever 430, a pixel that is exactly tuned, you know, or a laser beam, you know, some light emitting device that's exactly tuned here, and that's and one that's exactly tuned here. And if I adjust the energies of those, now this is at my sweet spot, right? The sweet spot of my long wavelength receptors, the sweet spot of each of these. But I am very precisely controlling the intensities so that I get the same sort of neural pattern here. So if I get this short wavelength to be about this much activity, and the green and the red to be about this much activity, it's exactly the same neural input to my visual cortex. It's exactly the same as if I had a laser beam of light right there. Okay, so this is how we're able to reproduce such a wide range of color hue experiences from a small number of light emitting elements, red, green, and blue. Okay, let's erase that. Clear all drawings. Good. Okay. I guess another example here. Okay, so yellow. I want to see what yellow looks like. Now, here's an interesting condition where once we are out beyond where the short wavelength receptors are really significantly active. So think about, you know, I don't know, about right, you know, close to 550, let's say, and up. Okay. From there, I no longer really have much input at all from my short wavelength receptors. I have only input from my long and medium wavelengths, and the relative input here matters a lot. So if I've got this much activity on my, let's do that again. Right. If I got that much activity on my long wavelength receptors, I've got this much activity on my medium wavelength receptors because I'm following that curve there. And I shine this laser beam in yellow. I say, yep, that looks yellow. But what this also says is if I have a combination of red and green hues, and I have the red be about this much stronger than the green, you know, maybe twice as strong roughly, I'm just approximating, then, okay, they're all drawings, advance. Then I could create exactly the same perception, okay? And I'll tell you what I'll do here. Let me pause it because I'm going to show you what that looks like with one of my art pieces. So pause recording. Oops. Pause recording, 1 second. Okay, we're back. Probably didn't expect this. This is Mr. Squee, my light Keytar. I invented it. So I'm going to show you how red and green light elements may appear yellow. Okay. Calibrate. All right, so I've got red and green light emitting buttons. I'm going to let the reds come in. I turned it off. Okay, turning it on now. Okay. And now we should get it. There we go. Oh, that's really bright. Okay, so what you see, all right, if I only let the green light come in, that's pretty nice, right? If I only let the red light come in, that's pretty red. Now I'm going to combine the red and the green. It's got an algorithm that makes it pulse in and out, so it's not going to be perfect, but, oh man, we are going to, at times, here, I'm going to try to hold this right up. Hang on. Wow, that's really bright, sorry. Okay, green, red, and then I hope that the yellow is coming through. This might not work so well with this really close, really super bright. All right, let's do one more. Let's add blue to it. And now you're going to see all the colors as it rotates through. So we've got, it'll turn white at times when there's red, green, and blue elements all active. I'm going to try one more time. See if I can get it close enough you can make out the individual light elements. Yeah, it might not work so well. All right. Well, thanks for letting me show off my beautiful instrument. Okay, thanks everybody. So red, green, so red, green, and blue light elements, all you need to make the entire visible spectrum. Okay, going back. All right, there we go. So again, this is the theory of trichromacy. Okay, so the idea of us seeing anything that we see is basically a product of the relative intensities of lights at different wavelengths that are picked up by our receptors, sent to the visual cortex, and interpreted along with all the other data as hues. All right. Now, one of the major topics that we talk about in human factors is the fact that not every human sees the same way. The interesting fact also is that we'll never know if we see differently than someone else until we get some specific testing, right? So some of you may have seen, let me just do this really quick. Okay, so color anomalous vision test images. This is it. So if you've ever seen any of these or looked at these circles and didn't realize what's the big deal, if you look at this and you see there's a circle and you don't see anything else in it, maybe talk to an eye professional. You may have some form of color anomalous vision. And essentially what these are designed to do is to identify people that have difficulty distinguishing certain hues. And if you say, well, this is green and that's red, and why could you not see that? Well, imagine that instead of red and green, you have some gradation of between red and green, brown, And each of these they might look a little different, but you wouldn't characterize this as red. You would just characterize it as brighter than this. Okay. So brightness and visibility are going to be there. But if we don't have exactly the same fully functioning 3 types of cone cells, we will not be what I call a fully functioning trichromat, and we will have trouble with certain comparisons of hue. Okay. And so we call that color anomalies or color anomalous vision. The term you hear, color blindness, is maybe that's the popular term, not accurate. You're not blind to colors. In fact, love to ask quiz questions, exam questions on this. So don't get confused by the term color blindness and think, oh, if somebody is red-green colorblind, they can't see red or they can't see green. It's not that they can't see it, as in they don't have a visual experience. They see the object. It's just that they can't identify whether the hue is red or yellow or green. So red and green have yellow in between. So between green and red, this is the entire part of this spectrum might be a problem. Okay. And the reason that occurs when we're talking about trichromacy is, again, because we're out beyond, in this range of light, we only have 2 receptors that are giving your visual cortex input. The short wavelength receptors are not active anymore. They're just like how when rods are your vision, like in scotopic conditions, and we have really deep reds, they're going to appear black. They're going to appear as the absence of reflected light, because if your sensitivity is based on the rods, you're going to be basically seeing things in this part of the spectrum, and anything outside of that is going to be just the absence of light. Similarly, in this range, if we don't have 2 fully functioning types of cells, the medium wavelength and the long wavelength, if these 2 don't function great, we're going to have a lot of trouble, because we have to compare the relative intensities of just these 2, because we're out beyond the short wavelengths, not contributing anymore in this range. But right here, and right here, my ability to distinguish the green from the yellow, orange from the red is all about the relative activity of medium and long wavelength receptors. Okay. If I am roughly equivalent medium and long wavelength activity, that's how my brain would interpret green in this sense. If I have roughly twice as much, like in this case, my brain would interpret that as orange or yellow. And, this sort of relationship, it would interpret as red. As it turns out, when we say color blindness, when we say color anomalies, the vast majority of genetic conditions in which we have an anomalous circumstance is because one of these 2, the long or the medium wavelength, is either missing genetically, people were born without it, or it's mutated in such a way that it doesn't produce the same level activity as a fully sighted trichromat, fully functioning trichromat. All right. So again, because of the relative activity, and when we have, right here, I've got 3 inputs, right? I've got 3 data points that are going to help me disambiguate what that color is. But out beyond the range where the short wavelengths work, I only have 2. And if one of those is sort of defective or doesn't function exactly right or is missing, now I only have 1 source of input, and that source of input can only tell me, is there light or is there not light? Is there light and how much? It can't tell me about the quality of the light in terms of what are the wavelengths. It just knows I'm getting some activity, my retina is active, so there's light there. But I cannot tell you, is that yellow, is that green, is that red? It's all part of this unicolor part of the spectrum between green and red. So if I look at a tree, if I have some form of color anomalous vision that is affecting either of my medium or long wavelength receptors, and I look at a tree as the leaves change from green to yellow to red, I would just kind of see them as, well, they're changing somehow, but I can't exactly tell you what I'm seeing that's different. It's not that they're invisible, right? Again, get ready for that on the quiz. It's not invisible. It's visible. I'm getting light. I just can't tell you, is it red or yellow or green. It's part of this part. It's this end of the spectrum where I cannot differentiate what the hue is if I don't have two fully functioning types of cone cells there. Okay, so I skipped a little bit here. Okay, so formally, color anomalous vision, not color blindness. You know, that's the more colloquial term. But we have two major types of this, and this is important to know because it affects a major percentage of the population. So we have mostly males in this class currently. There are 28 of you. That means, statistically speaking, a couple of you probably have some form of color anomalous vision. I've had lots of friends and close people in my life who have had this. Whenever I find out, it's great. I get to test them with all of the things I say in class. You know, hey, is this true? Oh yeah, it's true. You know, so I can speak with some authority on this. If any of you who have one of these conditions would like to talk about it, I'd love to talk about it. And it's, you know, health information, so I can keep it confidential. It just some people are really fascinated when they say, oh, I want to tell you about these glasses I use, for example, which help me. And then I can look into, well, how do those work? How do they help you? You know, based on what I know about trichromacy. So by all means, catch me in office hours or something if you want to chat about that. All right, so two major types. Either we have all three types of cone receptors, but one of them is wonky. And so we call that anomalous trichromacy. Okay, so trichromacy, I still got three, but one of them is wonky. Or dichromacy, and that means two. I've got two cones, two types of cones that are present. And it's almost always the short wavelength receptors, the S's here, are almost never affected. It's almost always the medium and the long wavelength cones that are affected. Okay. Why only males? Right. So it's because females can have these conditions, but you know, for those of you who took, you know, biology and how do genetics work, there's the trait that is carried with this visual anomaly is carried on the X-linked on the X chromosome. And so because females have two X chromosomes, it's much less likely you'll get each of those X's will have this trait. It can happen, but it's much less likely than having only one of them with that trait. And then a male can be born with just, well, they have just one X chromosome, right? So that's why it's much more likely for men. They only have one X and a Y. Women would need, you know, both of them to have the same rare trait. Okay, good. So color blindness usually doesn't, that's usually a misnomer. It can exist technically, but what this would mean is somebody might be born with no cone receptors at all, only rods, and rods can only deliver brightness. They don't differentiate based on the wavelength of light. You could probably get around the world just fine, you know, with rod vision. You wouldn't, it'd be different, but I think you could probably, you know, get around the world with that. So it's not the end of the world to be colorblind. And again, I want to hit this one more time. You know, it's coming on a quiz. It's not that somebody with any of these conditions doesn't see the light. They see light. It's not invisible. Invisible means absence of light. I'm not getting any action, right? It's the problem is in differentiating. I can see that light. I just can't tell you for sure if it's what you humans call green or yellow or red, because to my eye, it's all one consistent hue that's just brighter or darker. All right. Okay, so now within anomalous trichromatism, these are the terms that we use, the medical terms, to talk about what, you know, what's what here. If our long receptor is weak, or they use the term weak, but it fires at a lesser rate. It is somehow mutated. We call that protonomalous. So you know, the PROT. This is the prefix that goes with the long and the red receptors. Deuteranomalous, so deuter, that goes with green. So the medium wavelength receptors are weak or are malfunctioning. This is the most common form across all of them, you know, of what, you know, when people have color anomalous vision. The vast majority are deuteranomalous. seconded by probably Protonomalous. Very rarely, but can happen extremely rarely, we have a problem with the blue, the short wavelength receptors. This can develop with age. So I have, you know, the elderly aspect. It can develop. I don't know of anybody who's ever had this for real, though. It just comes from the textbook. All right. Dichromatism. So we don't have 3 functioning cones. We only have 2. And I'm either missing my long wavelength of light. So do I have any proto cells? Nope. I'm a protonope. Okay. So protonope is a descriptor for a person who is protonopic. Red-green blind, as in they cannot differentiate from red to green. Similarly, deuteronope is going to have the same problems. Okay. So that's kind of weird because I've got either I don't have a long wavelength or I don't have a medium wavelength. In either case, my problems become the green, yellows, and reds. And again, that's because I need both of these, the medium and the long. I need 2 inputs to really be able to tell you, is that green, is that yellow, is that orange, is that red? Anything out beyond the short wavelength active part of the spectrum, I've only got 2 things to rely on. If one of those is gone, then I cannot tell you is the light green or yellow or orange or red. I can just tell you the light is on. Okay. All right, good. Trichronope, again, almost, I've never heard of I've never heard of a case of this in life, other than it exists in medical textbooks, I suppose. So blue and yellow would be the differentiating problem there. All right, so this is Dr. Cope, you know, had created these images a long time ago. I like to use them just kind of as a mental exercise. I want you to, of course, recognize that assuming, okay, so first of all, assuming not everybody receiving this video or watching this video is a fully functioning trichromat. Some of you are probably having some form of color anomalous vision. This is going to make very little sense to you, and I apologize, but I'm trying to interpret for myself and for others who are trichromats what it might be like that a dichromat or an anomalous trichromat may see. So this is a rough, very rough approximation. Don't take this literally, but I'm just trying to get into your heads a little bit. All right, so we see all of these different colors of books on the table here. We see the deep red maroon of these chairs. Now, if I was protonomalous, so my long wavelength is not functioning like a fully sighted trichromat, then some of these reds are not going to get as much neural activity. I'm not going to get as much cone activity from some of these really nice vibrant reds like this book here. So it starts to look darker. It starts to kind of look into this brownish green, you know, I hope you can kind of see where here and here and here, these 3 books start to look more and more like a common hue that's just different brightnesses. And that's a good way to describe what's going on. The blue is still nice and vibrant. The blues are going to be really great no matter, you know, if you're protonomalous, deuteranomalous, protonope, deuteranope. If you have any problems with your medium or long wavelength cones, the blues are still going to be just great. So that's a nice, design sort of consideration, is if our population may include those with some form of color anomalous vision, blues are going to stand out from the background pretty universally, regardless of people's visual context. All right. Now, if we go from protonomalous, a weak but still existing red receptor, to a protonope or a protonopic, now here's a key. Now, remember this. Let's see if I got a slide for this. I don't. So I'm going to have to make one. Okay, so if you look at this representation up here. Now, if I take, let's say, I take my long wavelength receptor and imagine this thing is gone. It's not here anymore. Okay, so I'm crossing it out. Now, there is a part of the red spectrum, maybe about here, I'll just approximate. Everything over here no longer has a receptor that's giving you any input. If you're a protonopic, you're a protonope, This area of the spectrum does not have any cone cells that are going to be activated. So this is the one exception to my quiz question, which is trying to trick you about, hey, if somebody has a certain color anomalous condition, they cannot see reds or greens. And you'll say, no, wait a minute, Ferris told me, wait a minute, no, they can see them, they're visible, they just can't distinguish red from green. This is the one exception. If somebody is protonopic, meaning their long wavelength receptors do not exist, they are not physically present in any meaningful amount on the retina, then that means there is a range of the normally visible spectrum that these people cannot see, that become the absence of light, that become shining the TV remote in your eye and the infrared is not picked up by your eye. Similarly, if we were protonopic, this part of the spectrum would be the same as that light from the TV remote. So what you see here is our representation is that red, that vibrant red for a protonopic person would become the absence of light. It would absorb all of the visible light that is available for your eye if you're a protonopic person. So the reds become black, just like with the Purkinje shift. And our cones are no longer doing anything for us, and so the red flowers become black. Except unfortunately for these people, those red flowers will always be black. All right. So clear that. Go back. Good. All right. Deuteronomous and Deuteronomic, you'll notice, are not as severe as the Protonomalous Protonopic, because here now we're talking about the medium wavelength receptor, right? Sorry, I'm bouncing a little bit. And so if you take the medium wavelength and make that misbehave or take it out, we still get the full spectrum of activity. So still from 360 to 700 nanometers, we're getting some activity on the retina, even if we don't have a functioning medium wavelength receptor, because it's in the middle. But we will still have troubles where I need both medium and long wavelength input to differentiate the hue. So I'm still going to have troubles in this green, orange, or green, yellow, orange, red part of the spectrum. So I see reds here, but I think what we're trying to show here is that they start to get a little closer together. This is a little bit closer to the leaves are changing on the tree, and I can't exactly tell where it is. In fact, maybe, this is hard to approximate, but I would imagine these get even closer looking together, depending on how, I'm totally guessing, right? Because I have no idea. I cannot imagine very clearly what somebody else's visual experience is like. I only can imagine from my own visual experience. So this is our approximation, again, not to be taken literally, but these two get a little closer together, harder to view. And even more so if I have no functioning medium wavelength receptor, if I'm deuteronopic or if I'm a deuteronope. All right. So yeah, you can see those just kind of become this gray sand, right? All right. Okay, good, almost done here. So design implications, obviously we're designing for humans, a significant proportion of which may have one of these conditions. So there are some things we don't want to do, like have red layered on top of green. If you've ever seen like a really obnoxious, actually this is kind of painful. Let's see if we can find one. Let's see if we can find it live. Let's just go to a obnoxious Christmas red green website. So one of the things I tend to find once in a while around Christmas time is green text on a red background or red text on a green background. Not finding it right now, but you can imagine that might be problematic for somebody who has trouble differentiating which is red and which is green. To them, it'll be just like doing one of those color anomalous tests. You see the 8 within these, this splotchy image here. They just won't see it. So avoid that. As a designer, they could be red and green may be confused. Now you're thinking, oh, wait a minute, what about like red lights and green lights? Those should not be confused. You're right. So we have to think about that. Don't camouflage them. Yep, green text on a red background is awful. Yeah, so if we have color carrying an important part of our message, like stop your car or you can go now, red or green light tells us whether we can drive our motor vehicle or not in a lot of cases, right? So what about if you are color anomalous vision? I actually had the best man in my wedding. He was a roommate of mine first. He has one of these. He's red, green, color something. So I don't know if he's Deuteronomalous, Deuteronomic, Protonomalous, Protonopic, but reds and greens are his problem. And always a cool thing that would come up at parties, right? So, oh, you can't, you're red, green, colorblind? Well, how do you know if you can, how do you drive? How do you know when you can go or stop? And he would always say, well, I just like notice that all the other cars around me are going or stopping. and yeah, it's pretty reasonable. But the other thing is, of course, if he's all by himself, he can tell which light is what the signal is, because not only is the hue communicating stop or go, the position of the light is also fairly almost universally consistently up and down or left to right. I know that, you know, sometimes these are oriented that way, but there's a consistent ordering of the light. So the position of the light, in addition to the hue of the light, carry the message that's needed. So if somebody does have trouble differentiating red and green, a design solution here is, well, let's put those lights in different locations so that they could use the location to gain the essence of the message. Or another dimension. It doesn't need to be color or location, could be the size of the thing, could be whether it's flashing or not, but find another dimension that can convey the same information. So we called it, here's the key word, redundant encoding methods. Redundant is a lot of times used as like, oh, that's, you're writing something and you're using too many words, or you're writing the same thing 3 times, you know, in a paper. That's redundant. I'll use that term. But it's also, it basically describes the same message conveyed multiple ways. So redundant might mean you didn't need to go through all the effort. I got the message. But it might also mean I'm going to convey this in a lot of different ways because my users may need it in a lot of different formats to ensure that everybody gets the message. Whew. All right. So short break. Here's a little bit of fun for you. Now, when we talk about color and our perception of color, and brightness and our perception of brightness, this is a key point here. We always have to recognize that humans don't perceive things in isolation. They perceive things in context. And that context will include things like light sources. Okay. So let me stop at that for now and just take a minute and look at this and say, well, which one is brighter, A or B? And you're going to say, come on, this is easy, Ferris. It's clear B is way brighter than A. And I would say, are you sure? Oops. Because, you know, watch this, watch closely. Here we go. All right, now I'm not, you can see, I'm not messing with you. It's the same image. I'm just overlaying these things on top. And so now you'll note, oh, wow, that is the same shading. And what a powerful illusion this is. And how does this happen? And is because of what I was just saying, the context of the image matters. If I gave you these 2 stripes in this image and said, which one's brighter, A or B, you'd say, well, they're the same. But when I do this, your visual context includes a light source. So up here, if your video is the same as mine, the light source is essentially my video in the corner, and it's shining light down, you know, in this direction. And that light is, you know, there's a shadow cast by this shape. And so we interpret this region with a different relative brightness judgment because we realize it's in shadow. And this all happens effortlessly. It's not like we're doing a conscious, okay, well, that looks brighter, but it's in the shadow, so I better think of it as less bright. That's not how your brain does it. It just interprets the relative brightness compared to the context. You cannot easily remove the context from the way that you perceive a visual image. And this is me removing the context, or at least obscuring it to some extent. So without that, good luck getting your brain to agree with you when someone says this is the same hue, this is exactly the same shading as this. Okay. So we call this a brightness constancy. This is an example of a constancy, and it's an example of a brightness constancy. If I'm judging brightness, there is a certain way that I judge that brightness relative to the context. We call that the brightness constancy. The same thing exists for color. Okay, so here's an example of color constancy. So same picture, right? Under two different filtered lenses. And I hope you'll recognize this guy is literally holding the same pieces of paper. He's not tricking us, but it's just shot under different filters of light. Now, our brain looks at these pieces of paper and it interprets the hues of these paper relative to the context. The context, the surrounding image, is bluer than normal. So when we see these paper, we're going to interpret those hues relative to the background context of hue, the blue quality of the light. Similarly, with this one, we're looking at each of these, and watch this. I'm gonna hide the context, so you're only looking at the paper now. And when we have just these isolated images, we can see, well, these are not the same colors, not really, but in context, our brain interprets them as the same. Okay, or as pretty close. We can. It's believable for me to say this is exactly the same picture taken seconds apart or 1 second apart with just a different filter on the camera. That's conceivable, right? You believe me when I say that, even though when I do this and I say those are the same pieces of paper, you may say, well, wait a minute, I don't know about that. So this is an example, just like with the brightness constancy, the context of the lighting in that environment is always taken into account by your brain, which is interpreting what it's seeing. So another, a good example of this is you're outside. I mentioned that the sunlight is usually not. It's not exactly white. It's got some yellows to it. It's got a little bit of a redder tint than a lot of our interior lighting. And maybe you're outside wearing a bright green sweater, and the light outside is yellow. And you walk inside, and there's white light, and you're wearing a green sweater. And to somebody who could isolate the context like this, they may say, oh, you just changed your sweater between outside and inside. But that doesn't happen. People see a green sweater outside, they see a green sweater inside, even though if you were able to isolate the true light that's being reflected off of that, it might be slightly different, just like I show you here in this example. But the context, the lighting under which something is viewed makes a big difference in terms of how the human brain interprets the hue of that thing. All right. And here's another example of brightness constancy. So you have a nice bright baseball. It rolls under a bench and it's in shadow. Your brain doesn't interpret that as, oh, the baseball changed color. The baseball changed brightness. No, that baseball is still as bright as it was. It's just in a slightly less illuminated context. And so your brain effortlessly makes that assumption and that transition. All right, this may be familiar to some of you. I don't know how long this video will last. It may be a very dated reference by the time you see this. But this is something, a viral sensation about, I don't know, around 2020 or so, earlier than that, I guess, called The Dress. If you just Google The Dress, you probably get this. And the question is this a white dress with gold trim, or is this a blue dress with black trim? And that's a crazy question. And I'll let you debate that for a minute. You're going to say, well, it's obviously X. But then you may be very surprised to hear that for me, this has always been a white dress with gold trim. But probably for some of you, it's always been blue and black. And you're, how can that be? And a lot of it is, again, a color constancy and a brightness constancy sort of question. So I took the same image, I lightened it, and if you look at the assumed angle of sunlight, you allow more light to be seen in the image, so you expect certain hues and shades based on that light source. Or if you take that light source out of the equation and you darken it, now I can see where the blues and blacks come from. The interesting thing here is that however you saw this the first time, it's going to be very, very difficult for you to have a different perception of that. So I'm trying here to adjust to the lighting to show you how it might work, but you may be saying, no, it didn't really work. It's still blue and black, or it's still white and gold. It doesn't change at all. So you have to do some mental gymnastics sometimes to kind of get it to work. But the reason this effect exists is, again, it's a clear example of the context under which you're viewing this object, the brightness and the color quality of the light. All right. And I like to end this topic on hey, little small mind blower here. So just how we talked about, there's a significant population that does not have 3 fully functioning types of cones. There have anomalous, trichromacy, etc. There is also such a thing as a 4th type of receptor. Again, this is usually a genetic linked mutation based sort of occurrence, but there are a small number of documented cases of this where there's basically a mutated type of cone that sort of exists between the green and the red, or the medium and the long wavelength cone receptors. It only has been documented in females. So again, this is a genetic X-linked phenomenon. And if you want to check out this video, I think this one's in Korean, but it's or maybe Japanese. I'm sorry if I think it's in Korean, but that'd be terrible if it's in an Asian dialect that I'm unfamiliar, but it's subtitled. And if you watch this, you can see somebody identifying hues that, to my naked eye and probably all of yours, are almost indistinguishable. So if you look at these, makeup things here, to you and I and most of us would be like, yeah, those are all pretty much the same. I don't really see a difference there. Whereas somebody with tetrachromacy, 4 types of cones, may have a really heightened sensitivity to differences among this range of hue. So in between that green and red, that region might become extra sensitive if you have another data point for your visual cortex. So they have documented cases of people being able to, be much more easily differentiating some hues when they have this sort of condition. All right, that's it for section 2.3. Thanks.